Although most reactions tend to take place in solution, there are also some very important reactions that take place in the gas phase, particularly reactions that take place in our atmosphere. So I want to cover a little bit about measuring gases and the effect that has on stoichiometry to close out this module. Our learning goals are how to measure concentration in gas samples so we can use them to quantify the results of chemical reactions. We begin by considering the general properties of gases. And in order to consider those properties, we need to know the quantities that are most useful for specifying those physical properties. They include things like the pressure, the volume, the temperature, and the number of moles. And the variables that are used to denote each of these quantities are given here, as well as the units that we're primarily going to be using. Now, the key equation that you're going to need to know about gases is the ideal gas law, and many of you probably have seen it already. It simply says that pressure times volume is equal to the number of moles times the temperature times a universal constant, which is R, and it's given by this value when the units of liters, atmospheres, moles, and Kelvin are used. Bear in mind that if you're using some other unit of pressure or some other unit of volume or some other unit of temperature, although I don't know what that would be, then the value of R will have a different value. So we're going to stick with these units and use this particular value for R, but there are other values that can also be found. All right, now this natural ideal gas law, the most common form that we see it in is PV equals nRT, but I want you to be able to recognize it in a variety of different formats. For example, if we isolated the pressure on one side, it would be equal to nRT over V. If we isolated temperature on one side, it would be equal to PV divided by nR. If we isolated N on one side, it would be PV over RT. So these are all just different expressions of the same ideal gas law, where all we've done is a little bit of algebraic manipulation of the standard form PV equals nRT. Now, I also want to point out that pressure is a role that's very similar to concentration in solutions. So remember that molarity was moles per liter. Well, if we take the physical properties that we're using for gases and took moles divided by volume, which is moles per liter, we can actually manipulate the ideal gas law, and that's equal to pressure divided by R times temperature. Since R is a constant, it's basically saying that if temperature is also a constant, if we're dealing with something that happens at constant temperature, that the pressure is basically a good proxy for concentration. And the pressure is what's going to determine how concentrated something is and how readily it can react with something else. All right, now we also want to define something called standard temperature and pressure, because a lot of problems, a lot of situations take place using these particular conditions. They represent essentially standard conditions that you can think of as being sort of the average situation you might find at sea level. In particular, a pressure of 1 atmosphere, which is basically the pressure that the air at sea level exerts, would be the pressure for standard temperature and pressure, and the temperature is the freezing point of water. So we use these two to specify STP, STP standing for standard temperature and pressure. So one of the things that we might ask is, what is the volume of 1 mole of gas at standard temperature and pressure? So we would use a version of the ideal gas equation. We would solve for V. Okay, PV equals nRT, so V is equal to nRT over P. So it would look something like this. Okay, we're doing the volume for 1 mole, so the N is 1 mole. We have the value for R there. Standard temperature is 273.15. Standard pressure is 1 atmosphere. Now I want you to notice that in fact 2 of these items are 1, and the other 2 are the gas constant 0.082 and the standard temperature 273. The molar volume in this case is 22.4 liters, and it's useful to recognize that whenever we're at 273.15 Kelvin temperature, that R times that temperature is always going to be 22.4. All right, so a little something to stick in the back of your mind. Now I want to close by showing you an important result that is true for ideal gases. And I want you to suppose that the ideal gas that you have is a mixture of different substances. So it could be the air in the atmosphere, which is a mixture of oxygen, nitrogen, and some other trace amounts, carbon dioxide among them. So let's suppose we have a mixture of different substances. Now I'm going to just be very generic and say that N sub A gives the moles of A in the gas phase, and N sub B gives the moles of B, etc. And we're going to say that the sum of all of these components of the gas in the mixture add up to some total number of moles N. So the ideal gas law is actually going to depend on that total N. So P is going to be equal to the total number of moles times RT over V. Now what if I took that total number of moles and I wrote it out as that sum over the moles of different components in that mixture? So I might write this then instead. So all I've done is substitute, in the expression above where Na plus Nb plus ... equals N, I've substituted that thing on the left side for N in this ideal gas equation. Now I'm going to take this and I'm going to multiply it out. In other words, I'm going to take RT and multiply it by each of the items in that set of parentheses. So now I'm going to end up with a same expression here, but it's going to be Na RT over V plus Nb RT over V, etc., for all of the different components in that mixture. Now, you'll notice that each of those terms in the red side, each of those terms has dimensions of pressure. I mean, they're like a microscopic version of the ideal gas equation, but they are only including one of the components of that mixture. So I can actually define them as the pressure due to the molecules of A and the pressure due to the molecules of B. We call these partial pressures. They are not the full pressure, because the full pressure is going to be all of those things working together. They're just the pressure due to molecules of A or pressure due to molecules of B. But I can also, since all of this is equal to the total pressure on the left-hand side, I can now relate the total pressure to the sum over these partial pressures. And that's the key result that we wanted to get here. This is called Dalton's law of partial pressures. And it's true for an ideal gas, that basically if you have a mixture of gases, you can break it down and treat each individual component as though it is responsible for a certain fraction of the pressure.